Hello students, welcome back to my class. In today's lecture we will be studying about uncountability of sets. The first thing that we'll be dealing with is Cantors Theorem, named after the mathematician George Cantor, who was born in 1845 in Russia. He was a very famous mathematician, but unfortunately he was rejected, or his theories were rejected by mathematicians of that time. Nobody believed him. Just as you have seen in the earlier lecture, we had shown that there are as many real numbers as there are real numbers between 0 and 1. Okay, so these things are quite hard to believe, right? So mathematicians of that time also did not believe his theories about infinity, uncountability. Okay, and Cantor advocated the theory that there are many types of infinities. Okay, infinity is not the same, right? The infiniteness of the set of natural numbers is much different from the infiniteness of the set of real numbers. Okay, we have already seen that countable set of natural numbers is countable set, and we will see it in today's lecture that there are actually uncountable sets as well. So the second topic that we will be doing is uncountability of the closed interval 0 1. Okay, so Cantor he suffered from lots of depression because his theories were rejected, and he was labeled by the mathematicians of that time as a corrupt human being or a corrupt mathematician. Uh, so Cantor's life was quite pathetic. Okay, in fact, he suffered from various episodes of depression that increased in severity as the years passed by. So he was hospitalized several times for nervous breakdowns and spent the last 7 months of his life there. Okay, but gradually people came to recognize his theories, and the theory given by Cantor forms the basis of what we study now as set theory. Okay, countable sets, uncountable sets. Means set theory is very much credited to the George Cantor. Okay, he is known as the father of set theory. Okay, or founder of modern set theory. So he was one of the first to study the concept of infinite set in rigorous detail. Okay, so we will study these things in today's lecture. We will also see that the set of real numbers is uncountable. We will see that the set of irrational numbers is uncountable, and interestingly we will see that the set of real numbers is equivalent to the closed interval 0 1. Okay, so some of the equivalences we have already studied in the earlier lecture, where we have shown that any closed interval AB is equivalent to any other closed interval CD. We had also shown that the open interval 1 to infinity is equivalent to the set of real numbers. Okay, so these results are quite interesting. So let us begin with this remark that there are many different orders of infinity. Okay, and there are many types of infinity, what we will see in the Cantor's theorem. So if A is any set, then there is no surjection of A onto PA. Surjection means an onto map. Okay, so we could have stated it this way also. Then there is no onto map of A from onto map from A to PA. PA is the power set of A. Okay, so power set of a set cannot be equivalent to the set itself. Okay, this is the theorem. So let us see. Right, suppose that f from A to PA is a bijection. Surjection. Okay, that is onto map. Right. So one thing you observe, we can always define a 1-1 map from A to PA. Okay, that is quite simple. Right, you take A, each element of A to the corresponding singleton set. Okay, so small x goes to singleton x. Okay, that will give you a 1-1 map. So 1-1 map is always there, right? But there cannot be any onto map. Okay, that is what we will show, right? So suppose that f is an onto map, then for each x inside A, fx is a subset of A, because F is a map from A to power set of A. So for every element here in the set A, the image is an element of the power set, right? And an element of the power set is nothing but a subset of A. Okay, so that is why I have written this. So for each x inside A, fx is a subset of A. Okay, so there are two possibilities: either x is inside fx, right, or x is not inside fx. These are the only two possibilities. Okay, x may belong to that particular subset fx, or x may not belong to that subset, right? So let us denote by D the set of all those x in A for which x does not belong to fx. Okay, x does not belong to its image, right? So D is the set of all those x for which x doesn't belong to fx. So what is D? By definition, D is a subset of A, right? D is a subset of A. So that means D is an element of the power set of A. But remember that we had supposed that f is onto. So since f is onto, so there exists an element A inside capital A such that f of A is D, right? Onto means every element in the codomain will have a pre-image. So that pre-image we have denoted by small a, right? So again there are two possibilities: either A belongs to D or A doesn't belong to D. Okay, so if A belongs to D, then what happens? Then A belongs to Fa because D is f of A. Okay, but this contradicts the definition of D. What was D? D was the set of all those elements for which x doesn't belong to fx. Okay, so if A belongs to Fa, if A belongs to D, then by definition of D, A doesn't belong to Fa. But here we have got a contradiction because D is itself Fa. So we have got A belongs to Fa. So this contradicts the definition of D. Okay. So hence this option is not possible, right? A cannot belong to D, right? So let us see if A doesn't belong to D, then what happens? If A doesn't belong to D, then A doesn't belong to Fa because D is Fa. So A doesn't belong to Fa, but this is the very condition which is required to be satisfied in order to be an element of the set D, right? So A doesn't belong to Fa implies that A is an element inside D, right? So but then A doesn't belong to Fa, which implies that A belongs to D. This is by definition. So this is again a contradiction. We had started with A doesn't belong to D. Okay, we had started with A doesn't belong to D. Okay, but we have again ultimately we have got A belongs to D. So this is a contradiction. So thus we arrive at contradiction in all possibilities. Okay, so F cannot be onto. So we can never have an onto map from the set to its power set. Okay, so that means what? The power set of any set is much larger than the original set. Okay, A to PA, there always exists a 1-1 map. If we also have a onto map, then what will happen? We can construct a bijection from A to PA. But that's not possible. Okay, so the power set of A is a much larger set than A itself. So from Cantors theorem, we see that there is an unending progression of larger and larger sets. Okay, in particular, there cannot be any onto map from the set of natural numbers to the power set of natural numbers. Okay, so what we can conclude? We can conclude that Pn is uncountable set. Okay, a set is said to be countable if we can define an onto map from n to that particular set, right? That is already we had done the equivalent criterion for countability. So that means what? Pn is not countable because we cannot find any onto map from n to Pn, right? So hence Pn, that is the power set of natural numbers, is a much larger set. This is a very large set, right? Both are infinite, but the infiniteness of Pn is much different from the infiniteness of n. Okay, again P of Pn, that is power set of n. Okay, we can keep on constructing. Power set of n is also a set, so we can construct the set of all subsets of Pn, right? That is again a much larger set than Pn itself. So similarly, the power set of the set of real numbers is a much larger set than R. Okay, so even though both R and power set of R are infinite, the infiniteness of these two are much different. Okay, clear? So this is what was argued by Cantor, and this theory was very violently rejected. Okay. So now let us have a look at this theorem, how to show that the unit interval 0, 1 is uncountable. Okay, we cannot count. That means we cannot list the elements of 0, 1 as say x1, x2, x3 up to x that way continued. Okay, that means we cannot find any bijection from n to 0, 1. This is not possible. Okay. So for this we observe that every real number in 0, 1 can be written uniquely as 0.a1, a2, a3 like that in the decimal representation, right? That can be done where ai is an element inside 0, 1, 2 up to 9. That is ai is a digit, and we adopt some convention. We adopt the convention that a non-zero terminating decimal representation can be equivalently written as a non-terminating decimal by appending an infinite sequence of 9s. Okay, that is let me just explain with an example. For example, 1 can be written as 0.99999. Okay, that way we can continue. 0.5 can be written as 0.4999999. Everything goes on. Okay. Also, we adopt the convention that 0 is just written as 0.0000. Okay. So these are the convention. Under this convention, every real number between 0 and 1 can be written as uniquely as 0.a1, a2 up through like that. Okay. Now we suppose that 0, 1 is countable. Okay. So in the earlier videos you have seen if A is a countable set, then we can list the elements of A in some order. Okay. So then its elements can be listed as x1, x2, x3, x4 like that. Okay, can be listed, and we can write x1 as 0.a11, a12, a13, a14 like that. Okay, the x2 can be written as 0.a21, a22, a33, a4, sorry, a23, a24 like that. x3 can be written as 0.a31, a32, a33. Okay, so we are using matrix notation. So similarly, in general, xm can be written as 0.am1, am2, am3 like that. Okay. Now what we do, we show that it is possible to create a number in 0, 1 that doesn't appear in this list. Okay. We had assumed that 0, 1 is countable. That means every number between 0 and 1 can be written in this list, right? But we will show that we can find a number that is not inside this list. Okay. So how we can show this? We define a number y equal to 0.y1, y2, y3 like that by taking y1 as 2 if a11 is not 2. Okay, and y1 as 7 if a11 is 2. Right. We take y2 as 2 if a22 is not 2, and we take it as 7 if a22 is 2. Okay, in general, we take yi as 2 if aii is not equal to 2, and we take yi as 7 if aii is 2. Okay. So thus observe that y is not equal to x1. Okay, why y is not equal to x1? Because what is the first decimal, first place after decimal of x1? It is a11. Okay, so if a11 is 2, then y1 is 7. That means a11 is not equal to y1, right? And if ay1 is not equal to 2, then y1 is 2. So in this case also a11 is not equal to y1. So whatever be the choice for this y1, a11 is never going to be equal to y1. Okay, that means y differs from x1 in the first place after decimal. That means y and x1 cannot be equal, right? So y is not equal to x2 also, as it differs from x2 in the second place after decimal. Okay, y2 is not equal to a22. Okay, so in general, y differs from xi in the ith place after decimal. Okay, also since none of the digits in y is 0 or 9, so there is no chance that y represents an alternate decimal form of any of the xi's. Okay, so in fact we can define this number as yi equal to any number other than 0 and 9. Okay, because if you take 9, so there is a chance that the number y may be something like 0.999999, okay, and which is there in this list, okay. So it's not advisable to take 9, right? But if we take something other than 9 and 0, in that case there is no chance that the number that we have constructed represents an alternate form of another number in the list, okay. So you can take something like y1 yi equal to 1 if aii not equal to 1, 2 if aii equal to 1, okay, like that also you can take. So in any case we have seen that y is not included in the list, okay. So thus y is not included in the list, that means 0 1 is not countable, okay. Whatever list you create, we can always find out a number which is not there inside this list, okay. So 0 1 is not countable. Next, r is uncountable. So if this problem comes in exam, don't be happy with this 4 lines of proof. You have to first prove that 0 1 is uncountable, okay, and after that you have to apply the contrapositive of the result that we had done earlier. Every superset of a countable set, every subset of a countable set is countable. The contrapositive is every superset of an uncountable set is uncountable, okay. So you show that 0 1 is uncountable, and then 0 1 is a subset of r, so r is uncountable, okay. If the smaller set is uncountable, its superset will be uncountable. Then we can show that the set of irrational numbers is uncountable. So we know that the set q of rational numbers is countable. Suppose that the set of irrational numbers, that is r minus q, is countable. Then in the earlier lecture we had done one theorem that union of two countable sets is countable. So since union of two countable sets is countable, so q union r minus q has to be countable. That is, r is countable, but just now we have shown that r is uncountable. That means r minus q is uncountable. So the set of irrational numbers is uncountable, right? Now you observe that even though 0 1 and r, they are uncountable, they have the same size as 0 1 and r are both are uncountable, but even then they have the same size because 0 1 is equivalent to r. That is, we can construct a bijection from closed interval 0 1 to r, okay. How we can construct? Let us see this. So from the exam point of view, this result you may avoid, okay, but just for your interest I am showing you this result, how we can construct a bijection from 0 1 to r, okay. So first let us create a bijection from 0 1 to closed interval 0 1 to open interval 0 1, okay. So how we can do that? So we construct a function f from 0 1 to 0 1 as so we take 0 to half, we take 1 to 1/3, okay, and then for anything in between 0 and 1, we take fx to x if x is not of the type 1 by n for every n inside natural number, and we take fx to 1 by n plus 2 if x is of the form 1 by n for some n greater than or equal to 2, okay, right. So what do you see? Everything remains fixed except the numbers of the type 1 by n, okay, where n greater than or equal to 2. So half goes to 1/3, 1/3 goes to 1/4, 1/5 goes to 1/6, okay. This is what is happening. Everything else remains fixed. So here f is a bijection. So this is what is happening actually. 0 goes to half, right? 0 goes to half, 1 goes to 1/3, okay, 1 goes to 1/3, half goes to 1 by n goes to 1 by n plus 2, so half goes to 1/4, okay, 1/3 goes to 1/5, 1/4 goes to 1/6, okay, 1/5 it goes to 1/7, 1/6 goes to 1/8, okay. So that way this things 1 by 100 will go to 1 by 102, like that. So that way everything else will be in its own position, only these numbers of the type 1 by n will keep on shifting, okay. So we have a bijection here. So it's your exercise. If you are interested, you can try proving that it's indeed a bijection, okay, by formally proving that it is a bijection. So please try it if you are interested. Next, let us see this. So this we had done in the earlier class also, how to show that two intervals are equivalent. same type of intervals are equivalent. It's very easy. So g from 0 1 to minus pi by 2 to pi by 2 defined by pi x minus pi by 2. Okay, so I have done some rough calculation here for you to understand how this is happening. So we can go through this, and so this is the one definition part, and this is the on to part. Okay, and one part is very simple, right? So you can justify that g from 0 1 to minus pi by 2 defined by g of x is pi x minus pi by 2 is a bijection. Okay, so now we can find the composite of those two maps. F is a function from 0 1 to closed interval 0 1 to open interval 0 1, and g is a function from open 0 1 to open minus pi by 2 to pi by 2. So GOF is a function from closed interval 0 1 to minus pi by 2 to pi by 2. Okay, so it's a bijection. Again, in the last lecture also we had done h from minus pi by 2 to pi by 2 to r is a defined by hx equal to 10x. It's a bijection. So we can take the composite HOGOF from 0 1 to r is a bijection. So 0 1 is a equivalent to r. Okay, closed interval 0 1 is equivalent to r. Okay, and in the earlier classes we have already done any closed interval is equivalent to any other closed interval, any open interval is equivalent to any other open interval, and here we have done any closed interval 0 1 is equivalent to closed interval 0 1. So ultimately what you see, any intervals, you take any intervals in R, they are always equivalent, and they are also equivalent to the whole set of real numbers, right? Okay, so this was about your first unit. So we are done with the first unit from my portion. In the next lecture we will be starting with practicals for the differential equations. Okay, because colleges will not open till 17th May, on the third session of lockdown. Okay, so let us begin with our practicals. Till then, thank you.